we are given two arguments, num courses and prerequisites. Num courses is the total number of courses that you have to take, which are labeled from 0 to num courses minus 1. So if num courses was 6, then there would be 6 courses that you need to take, labeled from 0 to 5. Prerequisites is a 2D array that contains pairs of courses that tell you which courses are prerequisites of another. If it's possible to complete all courses, then we must return true. Otherwise, we'll return false. So for example, let's say this is our prerequisites array, and there are 4 total courses. The first item in the list indicates that you must take course 1 before taking course 0. You must also take course 1 before taking course 2, and you must take course 3 before course 1. Now, the fact that these prerequisites are given in pairs is a hint that we can express this problem as a graph. The first pair can be represented like this, where the nodes are the courses and the directed edge from node 1 to 0 indicates that course 1 must be taken before course 0. The second pair can then be represented with an edge from node 1 to node 2, and the last pair is an edge from node 3 to node 1. Now that we have the graph representation, we can visually see that to complete all courses, we would have to start with course 3, then take course 1, and then take courses 0 and 2 in either order. So since it is possible to complete all courses, we would return true. Now let's look at another prerequisite list. The first pair would be expressed like this, with an edge from 1 to 0. The second pair would be an edge from 2 to 1, and the last pair would be an edge from 0 to 2. But now we have a problem. We can't take course 0 because we need to take course 1 first. But to take course 1, we need to take course 2. But to take course 2, we need to take course 0. Because of this, it's impossible to complete all the courses, so we would return false. So you can see that what this problem is really asking you to do is to detect a cycle in a graph. If a cycle exists, then it's not possible to complete the courses and we return false. And if there isn't a cycle, then there's no problem and we can return true. So now the question is, how do we detect a cycle in a graph? There's a couple ways of doing this, but the method I'll be showing you is by using Kahn's algorithm to find a topological sorting of the graph. A topological sorting is an ordering of nodes such that for every directed edge u to v, node u comes before node v in the ordering. In other words, each node in the ordering must appear before any of the nodes that it points to. For example, for this graph, a topological sorting could be 3, 1, 0, 2, because 3 points to 1, and then 1 points to 0 and 2. Another valid sorting would be 3, 1, 2, 0, so there can be multiple topological sortings for a given graph. Now let's try to find a topological sorting for this graph. Well, we can't start with 0 because 1 has to come before it. We can't start with 1 because 2 has to come before it. And we can't start with 2 because 0 has to come before it. And we're stuck. So this is the key insight that we've been building up to. There is no topological sorting for a graph that contains a cycle. So our strategy will be to use Kahn's algorithm to find a topological sorting of the graph. If it's successful, then that means there is no cycle and we can return true. And if the algorithm fails, then that means we have detected a cycle and we can return false. So the last thing I need to cover before we go into the code is how Kahn's algorithm works. Kahn's algorithm works by using a queue to traverse and keep track of the nodes. The first step is to add any nodes with an in degree of 0 to the queue. As a reminder, the in degree of a node is the number of incoming edges to that node. So node 3 has an in degree of 0, and all the other nodes have an in degree of 1. So only node 3 gets added to the queue. The second step is to then remove the front node of the queue and visit it. So let's visit node 3. The third step is to then delete all outgoing edges from this node. So let's delete this edge. We now repeat these steps and look for any nodes that have an in degree of 0 and add them to the queue. We can see that now node 1 has an in degree of 0, so let's add 1 to the queue. Then we'll visit node 1 and delete all outgoing edges. So let's get rid of these two edges. Now both node 0 and 2 have an in degree of 0, so let's add both of them to the queue. We then visit node 0, which has no outgoing edges, so there's nothing to delete. Finally, we visit node 2 and we're done. The order in which we visited the nodes is the topological sorting, which was 3, 1, 0, then 2. And since we were able to complete the sorting, we know that there is no cycle in the graph and we can return true. Now let's look at a graph that does have a cycle. Again, we start by adding all nodes with an in degree of 0 to the queue. so that's just node 3. Let's visit node 3 and delete its outgoing edges. But now when we look for any nodes with an in-degree of 0, we see that there are none. This means that there is nothing we can add to the queue, and so since the queue is now empty, the algorithm ends without us being able to reach nodes 0, 1, and 2. And since we couldn't reach those nodes, the topological sorting fails, so we know that they were all connected in a cycle, and we return false. Now that we have everything we need to solve the problem, let's go look at the code in Python. Let's say that this is our prerequisites array, which means that this is the corresponding graph representation. We have 6 different courses numbered from 0 to 5, so num courses will be 6. First, we're going to create an array to keep track of the in-degrees of each node, and we'll initialize each element to 0. The indices will represent each node, and the value will be its in-degree. We're also going to create a 2D array and use this to create an adjacency list from the prerequisites. We're going to do this because it makes the graph easier to traverse, and it's one of the standard ways of representing graphs. The indices will represent the nodes, and the corresponding list will be a list of all its neighbors. Now let's loop through the prerequisites array to build the adjacency list. We're going to use a variable called prereq, which is going to be each inner list in the array. So now let's take a look at this line here. The element at index 1 of prereq is 0, which I'll highlight in green here. This corresponds to the index of 0 in the adjacency list, which I'll also highlight green. So this part right here is referencing the list at index 0 of our adjacency list. We're then going to append something to that list. So first, let's find the element at index 0 of prereq, which is 1, highlighted here. So we're going to append 1 to the list at index 0 of the adjacency list, like this. What we've done here is we've represented this edge going from node 0 to 1, and that's what this means. We're also going to increment the in-degree of the appropriate node. So again, the element at index 0 of prereq is 1, so let's increment the value at index 1 of in-degree. So now we acknowledge that node 1 has an edge going into it. Let's move on to the next pair. This is an edge that goes from node 2 to node 1. So again, the element at index 1 of prereq is 2. So let's find the list at index 2 of the adjacency list, and we're going to append the element at index 0 of prereq, which is 1. So we've added the edge from node 2 to node 1. Then we'll increment the value of node 1 in the in-degree array, since we added another edge going into node 1. And it's the same thing for the rest of the edges. We'll add an edge from node 3 to node 2 and increment the in-degree of node 2. Next is an edge from node 4 to node 2, and we'll increment the in-degree of node 2 again. Then we have an edge from node 5 to node 2, which brings the in-degree of node 2 to 3. Then it's an edge from node 1 to node 3, and we'll increment the in-degree of node 3, and finally an edge from node 5 to node 4, and an increment of node 4. Now that the adjacency list is done, let's create a queue. Now this is actually just a list, but we can effectively make it a queue by only adding nodes at the end and removing nodes from the front. We're then going to fill the queue with all the nodes that have an in-degree of 0. So let's loop through the in-degree array and see which ones have a value of 0. We can see that node 0 has an in-degree of 0, so let's append 0 to the queue. Next, node 1's in-degree is not 0, and neither is node 2's, and not for node 3, and not node 4. But node 5 has an in-degree of 0, so let's append 5. The last thing to do before starting the main algorithm is to create a variable called visited, which is going to keep track of how many nodes we visited. Notice that for this problem, we don't actually need the topological sorting itself. We just need to know whether it succeeded or failed. So because of that, we're not going to record the actual order of the sort, but rather, we're just going to keep track of how many nodes we visited to see if we were able to reach all the nodes in the graph. Now we enter this loop as long as the queue is not empty. First, we'll pop the element at the front of the list and call it node. So in the graph, we are currently visiting this node in blue. Since we've successfully visited a node, we'll also increment visited to 1. Now we're going to start deleting edges by decrementing the in-degree of each one of this node's neighbors. So in this line, since node equals 0, this refers to the list at index 0 of the adjacency list, which means neighbor will take on the value of every node in that list. which right now is just 1. So neighbor is 1. We're then going to decrement the in-degree of that neighbor, so the in-degree of node 1 goes from 2 to 1. By doing this, we are symbolically deleting this edge, like this. The last thing to do is to check if the in-degree of the node we just decremented is 0, because if it is, we'll need to add it to the queue. Right now, the in-degree of node 1 is still 1, so we skip this if block and move on to the next node. The next node to visit is 5, and now we visited 2 nodes. Now let's look at the neighbors of node 5, starting with node 2. Let's decrement the in-degree of node 2, which represents deleting this edge. The in-degree of node 2 is not 0, so let's loop to the next neighbor, which is 4. We're going to decrement the in-degree and delete this edge. But now the in-degree of node 4 has reached 0. So this means we need to append 4 to the queue, and then we'll go back up to the outer while loop. The node to visit is now 4, and we'll increment visited again. The only neighbor of node 4 is node 2, so let's decrement its in-degree and delete this edge. The in-degree of node 2 is still not 0, so we can't add it to the queue, and we'll just have to loop back again. But now notice that the queue is empty, which means this condition is false. So we're done with the algorithm, and we can just return whether num courses is equal to visited. In other words, if the total number of courses is equal to the number of nodes we visited, then that means we were able to find a topological sorting and there is no cycle. However, in this case, num courses is 6, and visited is only 3. So this last line is false. And that's because we weren't able to visit these 3 nodes because they are locked in a cycle. So since the topological sorting has failed, that means that we have detected a cycle in the graph. So we return false, which means that it is not possible to complete all the courses, and we're done.